Hello, everyone. So, your today class is going to conclude about IR spectroscopy and NMR spectroscopy. We have two sections. So, the first section is infrared spectroscopy. So, before focusing on IR spectroscopy, infrared spectroscopy, I'm going to mention about some instrumental methods for structure determination. So we have several methods. So one of them is NMR, or nuclear magnetic resonance, which I will talk about it in the second section of today's class. So NMR can provide extensive information about molecular structure and atom connectivity. So about the IR, which we're gonna talk about it in our first section of the class. So IR provides mostly information about the presence or absence of certain functional groups. So mass spectroscopy, which provide information about molecular mass and atom connectivity, and UV spectroscopy, which will give us some information about the presence of conjugated P system and presence of double and triple bonds. So about the IR spectroscopy, IR deals with the interaction of infrared radiation with matter. The IR spectrum of a compound can provide important information about its chemical nature and molecular structure. Usually the spectrum is obtained by measuring the absorption of IR radiation, although infrared emission and reflection are also used. IR spectroscopy widely applied in the analysis of organic materials, also useful for polyatomic inorganic molecules and for organometallic compounds. So, electromagnetic radiation is radiant energy having those properties of both wave and particles. Particles of electromagnetic radiation are called photons, and each has a discrete amount of energy called a quantum. Electromagnetic radiation can be characterized by its wavelengths and frequency. Wavelengths is the distance from one point on a wave to the same point on the adjacent wave. Frequency is the number of waves passing per unit time. It's reported in cycles per second, which is also called hertz. Energy of the electromagnetic radiation is directly proportional to frequency and inversely proportional to wavelengths. So, from a low energy to a high energy, we have different electromagnetic radiation, from radio electromagnetic radiation, microwave, IR, visible, near UV, vacuum UV, X-ray, and gamma ray. Each of them will have different effect on a molecule. So as I've mentioned, energy of electromagnetic radiation has a direct relation to frequency. However, it has a inverse relation to wavelengths. And as I've previously mentioned, wavelengths is the distance from one point on a wave to the same point on the next wave. So, for infrared radiation, the wavelength is between 2.5 to 17 micrometer. And the frequency is between 4,000 to 600. These frequencies make the frequencies of covalent bond stretching and bending vibration. Infrared spectroscopy can be used to find out about covalent bonds in molecules. In fact, by using infrared spectroscopy, IR spectroscopy, we can find some information about type of bonds which are in the molecule, which we have in the structure, and some other structural information. So this is the formula which you can calculate for the energy of the band. And so based on this formula, you can see that frequency is directly proportional to the strength of the bonding between the two atoms, K. And in addition, based on this formula, you can see that frequency is inversely proportional to the reduced mass of the two atoms. So in addition about the stretching frequency, so there are some parameters which are effective on the frequency. For example, by increasing the atomic weight, the frequency will decrease. Here you can see when we have a bond between carbon and hydrogen, the trim carbon, another carbon. So the atoms are being heavier, and so the frequency is decreasing. So with increasing in atomic weight, the frequency will be lower. So in addition, when the bond energy is decreasing, or I can say that when the bond is being much stronger, so because triple bond is stronger than single bond, so the frequency will increase. So with increasing in bond energy, with increasing in strength of the bond, the frequency will increase. So the frequency of a triple carbon bonds, carbon-carbon bonds, is much higher than the single bond. So infrared radiation is largely thermal energy. It induces stronger molecular vibration in covalent bonds, which can be viewed as springs holding together two masses. So, for example, here you can see we have a spring which is holding two masses. So, for IR spectroscopy, we will have something like stretching of the band of the spring, or compressing the spring which is holding two masses. Covalent bonds can vibrate in several modes, including stretching, rocking, and scissoring. The most useful bond in the infrared spectrum correspond to stretching frequencies, and those will be the one we'll focus on. IR radiation does not have enough energy to induce electronic transition as seen with UV. If the frequency of the radiation matches the vibrational frequency of the molecule, then the radiation will be absorbed, causing a change in the amplitude of molecular vibration. IR spectra are most commonly presented as percent light transmitted through a sample as a function of the wavelengths or energy of the light. Samples that absorb all of the IR light would give a spectrum with a horizontal line near the bottom of the spectrum. So, in an IR instrument, we will have IR source which will emit the IR light, and so the sample will absorb the IR, and so we will determine the transmitted light by using the detector. So here is an example of IR when we draw the graph based on absorption, but usually we use transmission for having the IR spectrum, transmission versus frequency in wave numbers. So we will have different kind of IR, a weak IR, a medium IR spectrum, or a strong IR spectrum, which I will show you some examples for each of them in next slides. So the point here is that just and only polar bonds will absorb the IR spectrum and will display bands in the IR spectrum. So, for example, we have a carbonated group, the CO group, because it's strongly is a polar bond, so we will have a strong IR spectrum. But for a triple CN bond, so the polarity is medium, so the IR spectrum will be medium. But for this compound, these triple carbon bonds, so the polarity is less and weak, so we will have a weak IR spectrum. But for a compound and for a bond like triple carbon-carbon in this compound, because it's completely non-polar, so we will not see any IR spectrum. Infrared band shape can be a narrow band or a broad band. So for broadband, I will show you in next slide. We will have OH bonds, in fact, in alcohol compounds. So that's a famous bond in IR spectrum. So the OH bonds will be a broad band. I will explain and show you in the next slides. So IR is most useful in providing information about the presence or absence of a specific functional group. In fact, by using IR spectroscopy, we are trying to find specific functional groups in the molecular structure. In addition to the functional group, we will have a molecular fingerprint area. So by using molecular fingerprint area, we can compare the spectrum, IR spectrum of our product and the spectrum in library and figure out which compound is the product which we have. So using IR spectrum is not difficult. It's going to be easy because we know the wavelength area and range for each functional group. So finding their bonds and their peak in the IR spectra is not difficult. So from 1,500 to 400, this is the fingerprint area. But usually we will have the functional groups bonds between 4,000 to 1,500 in this area. For finding the functional groups, we will focus on this area. But the 1,500 to 400 is the fingerprint area. So usually fingerprint area is a complex area, and its interpreting is not easy. But finding the functional group in this area from 4,000 to 1,500 is not difficult. So, for example, you know the wavelength area for OH group, and when you have a broad bond like this in the around 3,500, so you know that that's OH group. As I mentioned, so we will have the functional groups, and each of these functional groups will be shown in a specific range of the wavelengths. So based on that, you can recognize the functional group in the molecular structure. But about fingerprint region, so it's a complex region. So let's talk about interpreting some IR spectrum. So here is an example for alkane compounds. So here you can see we have CH stretch around 3,000. So it's a strong and sharp peak. It's related to CH stretch in alkane, about 3,000. But when we have alkane, so we will have a CH stretch around 3,080 next to that alkane CH stretch. That's a sign for having a double bond of carbon-carbon. However, in addition to it, we have this strong and sharp peak around 1,600, which is a sign for carbon-carbon double bond. So, but when we have alkene, so we have two signs. At first, the first one is the CH stretch from the triple bond of carbon-carbon around 3,300. In addition to that triple bond of carbon-carbon around 2,000. But here there is a condition. When our alkane is polar, a polar bond. But for example, here we have alkane, but the compound is completely a non-polar compound. That's why we will not see any triple bond CH stretch and triple carbon-carbon bond as we saw in the previous one, because here the triple bond is non-polar. That's what we cannot see. We will see these two significant signs and characteristic peak for alkane when the bond is polar. So about nitrile, so it's easy. For a triple carbon nitrogen bond, we will have a sharp peak and a strong IR peak around 2,200. And so when we saw it, it would be a nitrile group. It would be a C triple bond nitrogen. So as I mentioned about the alcohol group, OH group, it's very famous. Supposed to know that around 3,500, a broad peak means OH group in the compound. So about the aldehyde and ketones, so we will see another famous peak, a sharp and strong IR peak around 1,700. It's carbonyl group. So when we see CO, the carbonyl group around 1,700, so definitely is the compound is keton or aldehyde. So to recognize it's aldehyde or keton, it's easy. You can see CH stretch from the carbonyl group in the aldehyde, but around 2,700 and 2,800, this double peak. But here, as you can see in keton, we will not have it because we have not this bond in the structure. So when you saw these two famous peak, OH around 3,500, the broad peak, OH peak, and the carbonyl group around 1,700, so it means the compound is a carboxylic acid because you have OH and CO-OH group. So about amine, it's you can see a broad peak between 3,200 to 3,600, and so it's a sign of amine group, NH. And for amide, you will see NH stretch around 3,500 and 3,100. In this area, you will see this kind of peak, double peak, which is shown of NH stretch because you have NH2 here. In addition to the famous carbonyl group. So when you have carbonyl around 1,700 and the NH stretch peaks around 3,100 to 3,500. So these two peaks, 3,100 and 3,000, around almost 3,500. So it means you have an amide compound.